In this lesson, we're going to cover Unit 9, Acquisition 4, topic, Hess's Law. So first, what is Hess's Law? Hess's Law states, if a reaction is carried out in a series of steps, delta H for the overall reaction equals the sum of the enthalpy changes for the individual steps. So if a reaction occurs in a series of steps, we can calculate delta H for each of those steps, add them together, and that will tell me my delta H for the overall reaction. So why would we need to do something like this? This would be useful to calculate energy changes that are difficult to measure directly. So if we don't have a good way to measure the overall energy change for the reaction, but we can calculate the energy change for each of the individual steps, we could figure out our overall energy change. So first example. Given the following data, calculate delta H. You will see fractions for coefficients. That's fine. So this is like my master equation. I want to figure out my delta H for this overall reaction, given two steps. Carbon plus oxygen produces carbon dioxide with a delta H value of negative 393.5 kilojoules. And reaction B, carbon monoxide gas plus 1/2 oxygen produces carbon dioxide. This reaction has an enthalpy change of negative 283.0 kilojoules. All right, so what we want to be able to do is add these two reactions together and get our master equation. So it's kind of like a puzzle, and you just kind of have to think about it, try a few things, and see what happens. Just like when we were balancing redox reactions, remember that we can cancel out anything that shows up in both the reactant and the product side. So when I'm looking at this reaction, in my master reaction, I see that carbon monoxide is on the product side. But over here, carbon monoxide is on the reactant side. So what I need to do is flip this reaction. So I'm just going to reverse it. Anything that is on the right side of the arrow goes to the left side. Anything that was on the left side of the arrow goes to the right side. I'm going to leave this first reaction alone because I see carbon is on the left. I need carbon to be on the left. So I'm just going to rewrite reaction A. Now let's see if we can add these reactions together and get back to our master equation. So again, if you have something on the reactant side and it's the same on the product side, you can cancel it out. So here on the reactant side, I have carbon dioxide gas. Let's cancel them. I have one oxygen on the left, half an oxygen on the right. I could only cancel out half of an oxygen. So this coefficient will go from a 1 down to a 1/2. All right, now let's write what we have left. So on the left side of the arrow, I have solid carbon plus 1/2 oxygen gas on the right side of the arrow, I have carbon monoxide gas. So now at this point, my reaction matches my master reaction. So let's talk about the math. When equations are reversed, the sign of delta H is reversed. So we flipped reaction B. That means we need to flip its sign. So it is now going to be a positive 283.0 kilojoules. I did not do anything to reaction A, so I'm going to leave its delta H value alone. So we want to calculate delta H for the overall reaction. Well, Hess's law says we could just add these two together. 283 minus 393.5. Delta H is equal to a negative 110.5 kilojoules. Final answer. All right, let's try another one. Example number 2. Same question. Given the following data, calculate delta H for, so my master reaction and then we have two reactions, two steps, reaction A and reaction B. Okay, so the hard thing about Hess's law is I can't really give you guys steps. It's not like there's a spot that you should always start. We just kind of have to look at the master equation, and what I look for is, are the reactants on the right side, are the products on the right side? Correct side, I guess I should say. So for this first reaction, N2O4 is on the left side. In my master equation, it's on the right side. So I'm going to go ahead and reverse this reaction. When I reverse a reaction, I also flip the sign. So this now becomes negative. Looking at my second reaction, it looks like everything is already on the correct side. I want NO, nitric acid, on the left. I want oxygen on the left. It's already on the correct side. So let's keep this reaction alone and see what happens. Again, anything that is identical on both the left and right, we can cancel out. 2NO2 gas, 2NO2 gas. Let's cross those out. I don't see anything else that cancels, so let's bring down whatever is left on the reactant side. Let's bring down whatever is left on the product side. And if we did this correctly, our sum of the equation should be equal to our master equation. It is. So now let's go to delta H. So I already did the first one. We reversed the reaction, so I reversed the sign from positive to negative. We left the second reaction alone, so I am going to leave its delta H value alone. And again, Hess's law tells me that the overall delta H for the reaction will be equal to the sum of the individual steps. So 57.9 minus 113.1. Delta H is going to be equal to a negative 171.0 kilojoules. So let's try another example. So you might also have to multiply a certain equation in order to get the correct coefficients. So let's look at one like that. Given the following data, calculate delta H for 2 moles of solid carbon plus hydrogen gas produces. All right, for this one, we're going to have 3 reactions, 3 steps. So give me a second to get all of that down. Again, you will see fractions. reaction A, delta H, negative 1,299.6. That's kilojoules that I'm out of room on my paper. Reaction B, negative 393.5. And reaction C, negative 285.8 kilojoules. So this one's going to be a little bit more difficult for a few reasons. First, I already told you we're going to have to multiply our reaction by some number in order to get our coefficients to work out. The second thing that makes this a little bit more difficult is I see fractions that I have to deal with. And then lastly, we now have 3 reactions to deal with instead of 2. So let's just go through this reaction by reaction and see what we can figure out. So for the first reaction, notice in my master reaction, C2H2 is on the right. Here, it's on the left. So let's go ahead and reverse this reaction. Anything that is on the product side gets moved over to the reactant side. Anything that was on the reactant side, the left side of the arrow, now goes on to the right. Since we reverse the reaction, we also reverse the sign. All right, reaction B. I see carbon on the reactant side. Carbon is on the reactant side. That's good. But notice I need 2 moles of carbon and I only have 1 mole of carbon. So what we can do is multiply every single reactant and product by 2. That would give me 2 moles of carbon plus 2 moles of oxygen, producing 2 moles of carbon dioxide gas. Just like when we talked about heat and formation calculations, delta H is how much energy it takes to create 1 mole. Well, now I have twice as much. So let's multiply that delta H value by 2. When we do that, we would get a negative 787.0 kilojoules. Last reaction, reaction C. So again, I'm just going to look at this reaction and I'm looking for anything that's in my master equation. I notice I have hydrogen gas. I need hydrogen gas. I have 1 mole of hydrogen gas on the left side of the arrow, 1 mole of hydrogen gas on the left side of the arrow. Let's leave reaction C alone. Since I left this reaction alone, I leave its delta H value alone. Now let's go through and cancel and see if we ended up where we need to end up. On the left, 2 moles carbon dioxide gas. On the right, 2 moles of carbon dioxide gas. Cancel them out. 1 mole of liquid water. 1 mole of liquid water. Let's look at all of our oxygens. On the left, I have 2.5 oxygens. 5 halves is 2.5 oxygens. Cancel out 2.5 oxygens. Let's bring down whatever we have left. 2 moles of solid carbon plus hydrogen gas produces C2H2. Let's just do a double check. Does our sum of equations equal our master equations? It does. So then last step would be to take the sum of all of these. 1,299.6 sum of, so plus a negative 787 plus a negative 285.8. My delta H is equal to a positive 226.8 kilojoules. And then lastly, just to have this in your notes, we said when equations are reversed, the sign gets reversed. When multiplying an equation, we multiply delta H by the same number. So in order to get my 2 moles of carbon, I needed to multiply reaction B by 2, so I multiplied its delta H value by 2 as well.